Hey everybody, welcome to our session implementing an event-driven automation architecture. My name is Joe Pashota. I am a managing architect for Red Hat Consulting Financial Services, and this is Mike.
Hey folks, I'm Mike DeBosi. I'm a senior architect with Red Hat Consulting FSI as well.
And so what we're going to be talking about today is operations pipelines. And first, I want to have Mike walk everybody through the traditional operations workflow that we've all seen at most customers.
Yeah, sure. So we've seen a bunch of different operations workflows. We go from customer to customer, but like one we see a lot is actually diagrammed right here. So first thing that happens is a failure event comes in on a monitored system. So you've got some monitoring in place. It detects an issue and it triggers an event. IT gets notified about the event, and what they do is they usually create a ticket. Sometimes the ticket's created for them. Sometimes they have to go and manually create the ticket. It doesn't really matter. What happens then is that an IT contractor typically actually is assigned to the ticket, right? The contractor works the ticket for whatever length of time it takes to fix it. Sometimes it's a couple minutes, sometimes it's hours, sometimes even it's days. It depends on the issue. Eventually, the system gets restored to working order, and the IT contractor gets paid. So what are the issues that we actually see on a system like this? Well, the first thing we see a lot of times is that the mean time to resolution, what we call the MTTR, is very long. And there's lots of what we also call like in progress time here. So we're just waiting for the ticket to move from like one state to another. The second thing that we see a lot of times here is that there's no obvious institutional knowledge share. Every person that's working the ticket has a different way of addressing it. So one person, like let's say it's a ticket with the fact that there's a relatively low amount of disk space available on a device. So one contractor is going to go in and they're actually going to fix five places. Like they're going to address in 5 different places, like where it's got the disk is full. Another person is going to come in and fix 12 places. Another person is going to come in and fix 4. Another person will come in and fix 7. Everyone's a little bit different, right? And then the third thing that we see is that there's also a lot of times a loss of context between tickets. So issues are viewed atomically rather than holistically. Let's go back to the same issue there with regard to the disk space being full, right? Well, one of the things we see a lot when disk space is full is eventually the disk gets so full that that services stop. And when a service stops, you see another ticket for the service stopping. Well, the ticket about the disk being full and the ticket about the service stopping are actually related to each other in this case. But because you have different people assigned to different tickets, a lot of times that context gets lost. No one knows that like the issues are actually related to each other. And as a result, you get a bunch of churn in the processing of the ticket itself. So those are 3 things that we actually see as issues with the traditional operations flow.
Cool. So really what's happening in the traditional operations flow, though, is that you're having some tooling that somebody's looking at or that is automatically creating a incident or a ticket. And then that person is going to manually take that ticket and perform some remediation, either manually going into the system or running some sort of script to remediate. So there must be a better way to cause that, to create that logical gap between the incident and the automation.
Yeah, sure. So there definitely is. And one thing that we've seen work really well is event-driven automation or EDA. And at a very high level, what event-driven automation does is it replaces manual processes with automated workflows that are triggered by state changes. So when we say state changes, what we really mean there is exactly what we had in the previous, the traditional model, which is a monitoring tool on a host detects a failure event. Something has gone wrong. What you can do is you can actually take that event and actually route it into a messaging subsystem. Messaging can be whatever form messaging you want. Doesn't really matter. You then have some event consumers that come in and actually receive the messages, and what they're responsible for doing is they do some internal logic typically, but at the end of the day, what they're doing is they're doing routing. So they're trying to say, okay, based on this event and based on some metadata associated with the event, I want to call a playbook, a script to actually remediate this event, to fix the issue. And that routing can be, like I said, based on a simple set of criteria. It can be based on a complex set of criteria. It doesn't really matter. It's up to you. But at the end of the day, what happens is the routing actually is responsible for sending a message on to your automation platform. So for us, it would be like Ansible Automation Platform, and that actually is responsible for calling a playbook that actually fixes the issue on the system. And when you look at the issues that we've had in the previous model, they actually get solved pretty nicely here with this event-driven automation model. So first of all, the mean time to resolution is quite short, on the order of like seconds or minutes, not minutes to hours. The nice thing is that we have a heavily encouraged institutional knowledge share. So issues get addressed the same way every time. You have a playbook to do it. You have a script that actually is responsible for fixing the issue. That playbook can be shared. It can be modified. It can be reviewed by any number of people within your organization. And so that information is shared and is correctly perpetuated throughout your organization. The third thing that we see is that the ticket and action history are preserved. So you have that context information. Like you can say, okay, based on this particular event, let me look at other events that actually occurred in a similar time frame or in a relatively short time frame if you wanted. Maybe I want to run, playbook Y instead of playbook X if I saw a different event coming in the last like few hours or so. You have that power. You have that power at your hands, whereas before you didn't. And so that's the nice thing about EDA is it solves those three big issues that we actually had seen in the traditional model.
Great. So this model could really be used for a few different use cases. They all are going to have similar benefits, such as improved mean time to resolution, operational costs, and decreasing of outages. But the three different use cases that we wanted to discuss are automated patch management, self-healing infrastructure, and AI ops. The two that we're really going to discuss today are self-healing infrastructure and AI ops. In our experience doing self-healing infrastructure for companies, the solutions that we've developed have been extensible, meaning that it's allowing customers to control and expand their platform for event-driven automation. Continuous improvement, which is basically just that as the system grows, you're able to have that feedback loop and get those incidents remediated based on prior history. The systems have been designed for scale, meaning that they've been built on microservices that are containerized and able to scale horizontally. And the self-service component, which is really the ability to have a management interface where system administrators can go in and not only control and write those rules for this event-driven architecture, but also to go in and see a history of this system and truly audit it and change those rules based on what's happening. The second use case besides self-healing infrastructure that we're going to talk about today is AI ops, and AI ops is really an extension on that self-healing use case. The self-healing use case is going to be focused more around the rules creation and all of that experience, and then the AI ops is more based around using AI/ML to operate that system even more efficiently. I'll go into what that means a little bit later, but for now, let's talk about the self-healing infrastructure use case, and I'll let Mike describe in more detail what that is.
Yeah, sure. So at a high level, when we're thinking about self-healing infrastructure, what we really mean is an infrastructure that can automatically remediate through automation failure events that occur on member hosts. So the nice thing about that is it really addresses two key business challenges. The first is pretty obvious. It reduces maintenance costs, right? So you're taking a manual and externally mediated process with per ticket costs, and you're transforming that into a less costly automated process, right? So like you have playbooks doing the role of what your IT contractors would typically do in the past. And to give you an idea of the scale of these maintenance costs, we've seen large host estates in the past that have upwards of hundreds of thousands of, if not millions of tickets annually. So that it adds up very quickly. The second thing that it actually does is it also increases host reliability and consistency. So the nice thing about automation platforms is that they offer a reliable and predicted and most importantly documented way of addressing issues that result in less downtime and greater reliability. So you're not just reliant on contractors to talk amongst themselves and say like, hey, how did you fix this issue? Oh, I fixed it this way. Well, I fixed it this way. Okay, let's combine the two efforts, right? All of that stuff is stored in a repository. There are lots of people that can look at it in an SHI fashion. The rules are sacrosanct within the repository, and they can be modified as long as folks agree on them and things like that. But at the end of the day, like it's shared information amongst the entire team as opposed to just in an ad hoc fashion. So those are the nice things you see about a self-healing infrastructure, right? Like it's reduced the maintenance cost and also the increased reliability and consistency.
Great. So let's just go through the architecture. So from a high level, you have event generators on the left, which are picking up events from your systems, containers, network devices, whatever you're looking to monitor. It sends those events into an event bus, but it adds that layer of decisioning on top, having intelligent routing. You would also have, like Mike was saying before, an event history so that those rules can be based on history and actually based on context. And then from there, it kicks off actors, whether that's Ansible or container actions. So that's the high level architecture, but I want Mike to kind of take everybody through the more detailed technology that we used at our previous customers.
Sure. So I'm going to show you a couple slides that talk about an example architecture for SHI, and really at a very high level, there are two components that are important when you're constructing a self-healing infrastructure architecture. You have the runtime architecture, and that's basically the piece that is actually responding to events in real time, right? Like it takes in the events and ultimately like decides whether to send them on to Ansible for remediation or not. And then the second piece is a management interface. And that's the piece that allows people to control the rules that are actually like ultimately determining which playbooks are actually run based on events. And I'd like to focus on the runtime architecture first. So you can see right here, you have event sources coming in, and that's from your monitoring framework, basically like failure events coming in for a given host and whatnot. Those can get routed to a messaging layer. The messaging layer can be JMS, it can be Kafka, doesn't really matter. Basically, something that actually can pump messages into the system. At the other end of the messaging layer, you have consumers, and those are your microservices. And the microservices are responsible for a couple things. One is just the consumption of events, but then the second thing is that's where the actual execution of the rules logic actually happens. And so like within the OpenShift within the OpenShift environment, we have a intelligent router that like actually like looks at the rules that are actually within the system and determines one of two things. Like A, is there a playbook available to remediate this based on all the criteria we have? And B, if there's not a playbook available, should I actually create an incident, like a ticket off of that? And it goes through that logic. And let's say for the sake of argument here, or for the sake of a happy path, we determine that there is a playbook to remediate. Well, great. Then what happens is after we go out of the actual microservice layer, we go to Ansible Automation Platform, runs a playbook on the host. Everything is great. let's take the non-happy path. Let's say that there was no playbook to actually run through here. Okay, well now you have to decide whether you want to create a ticket or not. And we go through some logic there as well. There's, like I said, there's a bunch of different ways to determine whether or not you want to create a ticket or not. But if you did, you would actually interface with your ticketing system. You would create a ticket for the issue that was coming in. So at a very high level, that's the runtime architecture that you would look at for a self-healing infrastructure.
Great. So there has to be a management interface to actually handle these rules and actions, correct?
There is, yeah. So if you go to the next slide here, we're looking at an example for the management interface architecture. And there are a bunch of ways to write this as well. But at the end of the day, like Joe was saying, what you really care about is something that allows business users or ops users to actually modify and manage the rules themselves. What you don't want is a situation where you have to rely on the developers to actually manage the rules every time you actually want to make a change within the system. So we have a management interface that allows people to manage the rules however they want. And then new rules automatically get promoted into the system, and they are automatically, available for consumption by the system and for activation when new events come in. Like I said, there's a lot of ways to write something like this. One way that we've seen a lot of great success with is via the Open API framework and Vertex as well. But there are, like I said, a lot of different ways to actually write your management interface.
Cool. So besides the management interface, you're going to need an interface for your operations personnel to actually interface with what's been happening, the history of the system, as well as make any changes. So making the changes is handled via the management interface, but the ability to monitor a system like this is key, as the system is going to take actions on its own accord. So you need to be able to audit those actions and why they were taken. What we've developed at our customers is some dashboards for visualization of that logic that's happening and the automation that has taken place. At our customers in the past, we've used Kibana. It can be various different technology, but this is the stack that we've been able to work successfully with in the past. So what I wanted to talk about now is the maturity model for event-driven automation. This is really just a model to take a step back and look at where you think your organization is, whether you're still doing things completely manually or have some Ansible playbooks or automation to remediate issues, or whether you're actually already doing some sort of self-healing solution. The final step in this overall model is really AI Ops, which allows for AI/ML to modify how the remediations are taking place based on some predictive modeling. Obviously, AI Ops is not magical. You're still going to need to train your AI Ops solution on a history, which if you've already accomplished the self-healing type solution, you will be able to utilize that history from that self-healing solution to be able to train your AI Ops models. So I just wanted to discuss that as where you can go from here if you already are at the self-healing solution. And if you're not, we'd really like to hear some feedback and where on this journey you feel like you are. So thank you for joining our session today. If you have any further interest in the solutions that we've discussed, please don't hesitate to reach out to your Red Hat representatives, and have a wonderful rest of Ansible Fest. Thank you all for joining.